Okay, so we're still talking about quadratic reciprocity, of course, which is this nice result that tells us for Q and P odd primes, tells us that the Legendre symbol QP is equal to the Legendre symbol PQ. So it takes a minus sign in front of it if P and Q are both congruent to 3 mod 4. But otherwise, it's just equal to the Legendre symbol PQ. Remember, every odd prime is going to be congruent to 1 or 3 mod 4. So there's 4 possible combinations for the status of P and Q. One of them, when they're both congruent to 3 mod 4, the Legendre symbols have opposite sign. So they have opposite status as quadratic residues modulo one another. But otherwise, if at least one of them is congruent to 1 mod 4, then they both have the same status modulo the other. They're either both non-residues modulo each other, or they're both residues. So it's a very nice result that tells you how their two statuses relate. Now, I've hummed and hawed a bit over this. The proof of quadratic reciprocity is in the book, but we've gone some way towards it, but I don't think I'm going to kind of labor through every little part of it, because I think it's better to look at uses of quadratic reciprocity and just to spend some time thinking through the problems that are asked about it in the tutorial exercises. But just to give a very quick overview of how the proof proceeds. We kind of approach the proof in the book quite gingerly, with lots of preparatory results. So the first result is the first result was Euler's criterion, which told us how to evaluate an arbitrary Legendre symbol. It told us it was going to be congruent to whatever the argument n was to the power of p minus 1 over 2 modulo p. That gave us a nice way to think about Legendre symbols and build arguments based on them. Then we had theorem 8.7 due to Gauss. Gauss's criterion. Sorry. Yeah, criterion. For Gauss, where you looked at the Legendre symbol NP, and it told you this was minus 1 to the power m, or minus 1 depending on the parity of m, where m was the count. It's a bit of a mouthful to write out, but this is the count of the multiples j times n, where, and you're taking every multiple between 1 and p minus 1 over 2, count of the multiples of Jn, where J is that, which have a residue, which have a standard residue modulo P, which is greater than P over 2. So you're looking at all the multiples of n, taking their standard residues modulo P, meaning the smallest remainder after division by P, and the number of these that fall in the second half of congruence classes, in the top half, greater than P over 2, that number m, the count of the number of those, gives you this exponent on the minus 1. And we did actually work through the proof of that. And it's just kind of keeping track of all the minus signs flying around and just kind of carefully enumerating. Again, it's based on Euler's criterion, the proof of that. So all those results we've kind of fully considered through the proofs of them. Theorem 8.8 focuses on this number m. So this is the one I'm just going to just basically look at the statement of the results of and then see how that's applied to prove the quadratic reciprocity. Well, in the case for odd n, which in the case in interest, when we come to tackle quadratic reciprocity itself, we're talking about odd primes. So either argument to the Legendre symbol is always going to be odd. But this theorem gives you like a very intriguing formula for this number n. Okay. So in this result here, you just have to separately examine all these multiples, just laboriously reduce each one mod p, find out which ones have the large residues, and count the number of those. But theorem 8.8 gives you something of a formula for this. Remember, we aren't particularly interested in the precise value of m, just if it's odd or even. So that's the only thing that's going to affect this value here, -1 to the power n. So theorem 8.8, and you can see in the proof of theorem 8.8, it's summations all over the place, and you've got separate summations covering things with positive sign and minus sign. These are separate summations covering things that land in the top half versus the bottom half of the residue class. And what this establishes is this nice formula for m modulo 2. And knowing something modulo 2 is knowing whether it's odd or even, whether it's divisible by 2, congruent to 0 mod 2, or odd when it's congruent to 1 mod 2. And again, this just covers the j's, first half of kind of coefficients from 1 to p minus 1 over 2. And you're looking at this quantity here, just sometimes written as proper square brackets there, sometimes square brackets, but just with the bottom inward-facing feet on them, where this function, this is the floor of x. And the floor of x is the largest integer less than or equal to x. Okay? So when you're looking at these multiples, are Jn, and this is just a regular fraction, nothing like a Legendre symbol or something, just the regular fraction Jn divided by p. So that's probably not going to be, not going to be an integer in most cases. So, in fact, in kind of all cases under consideration, it's going to be a fraction, but this is the notation for the floor of a real. And then once you have all of those, so I'll leave you to read through the proof of that yourselves. As I say, it's not something I want to tackle full on, all the bits and pieces of it. But it establishes this formula for n, and that allows us then to give the final proof of quadratic reciprocity. But I would just like to say a few words about that because it has this appealing picture associated with it. First of all, the way the result is proved is by establishing this equation here. So the first task is to see that this equation is equivalent to the law of quadratic reciprocity as we've stated it up to now. So this is stating it in a different way. So this talks about the product of the two Legendre symbols. Take the Legendre symbol from the left and the one from the right, multiplying them together. Now individual Legendre symbols are either plus or minus 1. So the product is going to be plus or minus 1. If you're in the otherwise case, if one or both of the p and q are congruent to 1 mod 4, then they have the same value. So they're either both plus 1 or both minus 1. So in that case, the product of them is going to be plus 1. Whereas in the other case, where they're both congruent to 3 mod 4, they carry opposite signs. So the product of them is going to be minus 1. Okay? One of them is going to be plus 1, the other one is going to be minus 1. So the product of them is going to be minus 1. That behavior of giving a plus 1 value when one or both of the P and Q are congruent to 1 mod 4, and giving opposites, giving a minus 1 value when both of them are congruent to 3 mod 4, this is captured by this power of minus 1. So it's minus 1 to the power of product of two things, P minus 1 over 2 times Q minus 1 over 2. You see, if either a P or Q are congruent to 1 mod 4, then let's say it's a P, then when you subtract 1 from it, P is congruent to 0 mod 4. So it means P is a multiple of 4. So when you divide it out by 2, it still leaves behind an even number. Yeah. So if you're a multiple of 4, you cancel out one of your 2's, you still got at least 1 2 left behind. So you're still an even number. So if one of them is congruent to 1 mod 4, there'll still be an even number here as one of the factors in the exponent. So overall, you'll have an even exponent, taking that power of minus 1, so you'll get plus 1. In the case where they're both congruent to 3 mod 4, then when you subtract 1 from them, they're congruent to 2 mod 4. And something congruent to 2 mod 4 means it's a multiple of 4 plus 2. When you divide it out by 2, you get a multiple of 2 plus 1. So you get an odd number. Okay. So when they're both congruent to 3 mod 4, this fraction P, well, this integer P minus 1 over 2 is going to be odd. And so will Q minus 1 over 2 be. That's congruent to 3 mod 4. So the overall exponent is a product of two odd numbers. So the overall exponent is odd. So you've got an odd power of minus 1. So you've got minus 1. So the first thing is just appreciating that this kind of two-case version of stating the quadratic reciprocity law is equivalent to this. Okay. When you got these things being plus and minus 1, there's many different ways to kind of present the same thing. And so the reason this is useful is it suddenly gives you a new viewpoint on the thing, because simple products of quantities like that, geometrically they correspond to areas. Or well, we're not quite doing continuous stuff here, we're doing discrete stuff here. So taking products of numbers like that corresponds to counting things, counting dots in an integer lattice. So this is how the proof of or this version of the proof of quadratic reciprocity is presented. Quadratic reciprocity is one of these things where there's loads of different ways of proving it, and we're kind of collecting proofs. This talks about the integer lattice, or the integer lattice in the plane. Now, for our purposes, we can just regard the integer lattice in the plane as just the collection of all points which have integer coordinates. Okay, integer x coordinate, integer y coordinate. So it's a set of dots in the plane. Okay. And what we're doing here is we've plotted the pair of values P and Q. So P and Q, actually I should fill in that dot as well. That should be a black dot there. So that's one of the integer lattice points, PQ. It's got integer coordinates. And now that quantity, that product of, so we had PQ, QP was minus 1 to the P minus 1 over 2, Q minus 1 over 2. This alternative version of the quadratic reciprocity law. You look at this product of the exponents, P minus 1 over 2 times Q minus 1 over 2. So these are these 2 points here. So we got a P axis kind of and a Q type axis. So the number of lattice points in the interior of this square is equal to that product, P minus 1 over 2 times Q minus 1 over 2. Okay? Because you've got 1, 2, 3, 4, all the way up to P minus 1 over 2 columns. And you've got 1, 2, 3, 4, all the way up as far as Q minus 1 over 2 rows. Okay? So how many dots are there in total? Well, it's the number of columns times the number of rows in the interior of the square. So the number of integer lattice points there is equal to this equal to the product of those two. So is the exponent on -1. So that's one way of counting. If you want to count things in a rectangular piece of an integer lattice, you just multiply the number of rows by the number of columns. But there's an alternative way to count it, and that's to take this line, which goes from the origin through PQ, and to add up the number of things in the top triangle plus the number of things in the bottom triangle. Now, the first thing to say is that this line here cleanly divides the lattice points. This line does not intersect any lattice point. Except for the first lattice point, if you travel out from the origin, the first lattice point that it intersects is the one with coordinates PQ up there. Okay, and that's because P and Q are primes. Okay. Remember, if you think about a line, the gradient of a line is the ratio of its x and y of its y over x coordinate. So this line is gradient Q over P. Yeah. If there was an earlier lattice point that it intersected, a point with coordinates less than P, x coordinate less than P and y coordinate less than Q, then you could express the gradient of this line as the ratio of those two integers. So in effect, you'd have another fraction of integers, which is equal to that fraction of integers. So what you would have done is you would have discovered some kind of factor that you could cancel out the P and Q. But that's nonsense because the P and Q are both primes. So they certainly have no common factor apart from one. Okay, so both prime numbers, they're both two distinct prime numbers. So that's why that this line cleanly divides those lattice points. So there's a collection of points in the interior of the top triangle and a collection of points in the interior of the bottom triangle. And we count the points in the two triangles that way. And the reason we count them that way is because that brings in this quantity here. Okay? Because these quantities here relate to the number of lattice points that are in these rows or columns. So we have this result that the number of things in the interior of the rectangle is the product of these two numbers. That's just based on the simple principle of number of rows by the number of columns. But then you start to count the things in the triangles. And let's say, I'll do it for this one. If you're counting the number of things in T1, you count the number of things in T1. T1 is the lower triangle. You count them column by column. So you say the number of things in the first column, plus the number of things in the second column, plus the number of things in the third column, and so on. Now, what's the last point you get up along here? The number of points in a column in T1. Let's say the column located at point T. You see the top point on the line, Q over P is the gradient of the line. So the y coordinate, you might want to add this in, the y coordinate of the point on this line. Now it's not a lattice point, it's not a point with integer coordinates, because there is no point with integer coordinates on the line before that one, PQ. But the coordinates of the point on this line here above T, the y coordinate is exactly this quantity TQ over P. Okay? Because it's the gradient Q over P times the horizontal coordinate T. Remember, this is a line which goes to the origin. So the equation of the line is simply y equals the gradient times x. There's no intercept. Yeah, y equals the gradient times a. So how many things are in this column? Well, there's 1, 2, 3. So all the time you're counting up along the vertical axis. 1, 2, 3, all the way up until you get to this last one. And this, by definition, the y-coordinate of this last integer point in this column here is the floor, the largest integer less than or equal to the actual y-coordinate of the point on that line there. I still want to put a big dot there, but I'll get in trouble if I do. So it's the floor of this quantity, which is the points in column T, the column over the point T in T1. So in effect, then, the number of points in T1 is basically this quantity here. So if you look over here on the page, the number of points in T1 is M1, is this quantity here, which is this formula here with the n replaced by q. And then when you count the number of points in T2, the top triangle, you count them row by row, you get a similar quantity talking about the floor of these multiples of P over Q. And so by looking at the result of that theorem 8.8 then, you get that the Legendre symbol PQ is going to be -1 to this power n2, and QP is going to be -1 to the power m1. Okay, so it's the presence of those expressions, those summations of floor values of multiples of the gradient of the line, which theorem 8.8 tells us gives you, once you interpret it modulo 2, gives you the parity of this number m, which gives you the exponent of -1 for the value of the Legendres. So these two Legendre symbols are equal to those two things. So when you multiply them together, then you're multiplying together those two powers of -1. So you're simply getting m2 plus m1 in the exponent. m2 plus m1 is the number of points in the top triangle plus the number of points in the bottom triangle. So it's the total number of points in the rectangle, which we've already decided just by very simple considerations is just the product p minus 1 over 2 times q minus 1 over 2, the number of rows by the number of columns. So that's just a quick overview of how the proof is put together. It's kind of intriguing and strange in some ways that we suddenly switch to giving geometric type arguments or building arguments in terms of what's going on with points in the plane. So that's an intriguing connection, which in some way gives you a flavor of a lot of the connections that there are between all different branches of mathematics. So like sometimes we regard geometry as this kind of separate stream of mathematics, and number theory is this kind of separate stream, and analysis or calculus is this other kind of separate stream. But they all constantly have links to each other. And very often, you know, significant progress is made in mathematics when new connections are discovered. Okay? So number theory, advanced number theory splits into two main kind of streams called algebraic number theory and analytic number theory. And algebraic number theory is all about applications of algebra and group theory and rings and fields to number theory. The analytic number theory is all about applications of calculus and analysis, complex analysis to number theory. And you know, you're getting a taste of some of those connections that there might be because of this kind of some intriguingly simple geometrical arguments in terms of counting things in rectangles and triangles that somehow gives you a clue to how to establish this very important number theory. Okay. So the fine details are all there for you to read through. But as I say, I didn't want to kind of focus on the dotting every I and crossing every T. I would rather spend time discussing some of these remaining applications and problems. So I'll take the first one here. So this is in exercise 8.5. You should be aiming to, deal with all of these questions as part of your, part of covering this topic. And certainly, see, I've asked a number of questions here about practicing the evaluation of, more or less arbitrary Legendre symbols. Remember, we had that reduction type algorithm similar to the Criterion algorithm, so that's quite a key skill to be able to do that. And it's a nice question because in order to evaluate those, you need to use lots of the basic properties of the Legendre. So it's a good application. Okay, so here's this first question on 8.5. So this is a nice question, and it returns to a theme which I stressed at the beginning when we were discussing quadratic residues. Do you remember when we introduced quadratic residues, we connected it to the concept of square roots, because it is basically talking about the existence of square roots and which numbers are squares and which numbers aren't. Then we've got a pretty good understanding of the criteria for real numbers and normal square roots. Okay? Positive real numbers have square roots, negative ones don't. Okay? And positive and negative numbers have this multiplicative structure. When you multiply two positives, you get a positive. You multiply two negatives, you get a negative. You multiply two, you get another positive. You multiply two negatives. When you multiply one of each, positive times a negative, you get a negative. We discovered, and it was one of the first things we proved about quadratic residues, that quadratic residues have that very same property. You multiply two residues in the system set, the multiplicative system Zn. You multiply two residues, you again get a residue. You multiply two non-residues, you again get a residue. That's like multiplying two negatives, you get a positive. You multiply one of each, a residue times a non-residue, you get a non-residue. So that was very satisfying to see that structure, that multiplicative structure, was possessed as well by the multiplicative system Zn. Okay. Now, question one is kind of examines this further. So what you've got there the negatives and the positives gives you what is called a partition, splitting into two clean subsets of the non-zero real numbers. So you can express the real numbers as 0 union all the positives, union all the negatives. Okay? And importantly, the positives intersect the negatives is of course empty. Okay? These two sets are disjoint. Okay? Well, in ZP, integers modulo p we have the quadratic residues and the non-residues. And, well, if we also consider 0 mod p, so this is standing for, okay, the integer 0, but also every multiple of p. Remember, the multiples of p aren't members of the multiplicative system of integers under multiplication modulo p. So we exclude those because they don't have multiplicative numbers. And again, residues intersect the non-residues. Again, that's empty. I mean, residues and non-residues are opposites of each other. Exists a square root, does not exist a square root. So it's really opposites. Well, what this question is saying is basically this is the only way that you can partition the elements in ZP in such a way that is a partition, but that also has that multiplication structure. I think they're called S and T. So we suppose, maybe we could what if you could partition the elements of ZP into one set S, one set T, and they don't overlap, they're completely disjoint, and for every pair of elements S1 and S2 and S, the product S1, S2 is again an S. For every pair of elements T1 and T2 and T, the product T1 times T2 is again an S. This is the multiplicative structure that residues and non-residues have. And if you take for every T1 and T, an S1 and S, you take one from each, you take the product, you get an element of T. Are there any other ways of doing this apart from the way we already know about, which is splitting it into the residues and non-residues? Okay, that's the question. Now, the reason this is an interesting question to think about is we already stressed the niceness of having the residues and non-residues playing the role of positive and negative numbers. But that, yeah.
Is that supposed to be S1 and S2? You've written S1 and S1.
Oh, yeah, sure. Okay, yeah, sure. So that's nice that the residues are playing the role of positives and negatives. But that connection would be weakened somewhat if if there was loads of other ways to do this as well. But if there isn't loads of other ways to do this, if there is only one way to do this, which is with S being the residues and T being the non-residues, then that kind of gives you a lot of information about ZP, knowing that it can only be split, can only be partitioned with this multiplicative structure in one way into the residues and non-residues. That gives you some kind of a uniqueness information about ZP. Well, the question kind of, one way you might have asked this question is just still with the question mark, investigate this, are there any other ways? But I think the question directs you to prove that there isn't. Okay? So it says, prove that there's only one way to do this, that if you have a system that satisfies this, it must be the case that, in fact, S consists of the quadratic residues. All the n's which have Legendre symbol +1, i.e. all the residues. And T must consist of all the n's with Legendre symbol -1, i.e. the non-residues. Okay, so we can have a look at the proof of this. So any questions just about the setup? Oh, I think part of it as well is that S and T are, S and T are both non-empty. Yeah, these, like if T was empty, this would be trivially true because these are quantified, saying for every T and T, for every T and T. If T happened to be empty, there'd be no instances of this. So these would be trivially true, miraculously true. So we assume that S and T are both non-empty. Okay, we've already seen that the residues and non-residues satisfy the multiplicative conditions. Okay, we proved that in the early days of our look at the residues and non-residues. So now suppose S and T satisfy the conditions. The conditions shown in the question. And consider any n in ZP in the multiplicative system. But since S and T partition ZP, so this is one where P does not divide N. Clearly, N is an element of S or N is an element of T, as ZP is equal to the union of S and T. But in both these cases, see if you take two things from S and multiply them together, you get an element of S. So in that case, N squared is an element of S. But also, if you take two things from T and multiply them together, you get an element of S. So in this case, if N is in T, the square of N has to be in S. So N squared is in S or N squared is in S. So in other words, N squared is in S. That's the conclusion. For every N in the multiplicative system mod P, N squared is in S. So this, therefore, that shows that S contains all the residues. Okay? Because the quadratic residues are the things that look like this, look like the squares. So they're all in S. Okay, let R1 up as far as R to the P minus 1 over 2 be the residues. These are all, now we know, elements of S. And we let T be any element of T. Remember, part of the condition is that T is not equal to the empty set. So there is a T in T. Clearly, T is a non-residue. Yeah, that was something we proved early on, that if you, that there are only P minus 1 over 2 quadratic residues. Half of the elements are quadratic residues, half of them aren't. So if we've already discovered that all of the quadratic residues in S, anything in T has to be a non-residue. And then consider the elements TR1, TR2, just consider these products. T times R to the P minus 1 over 2. So here, these are products of one element from T with one element of S. So these are all elements of T because of this last multiplicative property. Take something from T and something from S, multiply them together, you get an element of T. These are all elements of T. And they are all non-residues, since the residues are all in S. We've already described. And there's p minus 1 over 2 of them. P minus 1 over 2 is the count of the number of these. 1, 2, all the way up as far as p minus 1 over 2. So i.e. all the residues are, sorry, all the non-residues are in T. So that proves that S and T are his claim. S has to be the residues, T has to be the non-residues. There are no other elements. S equals the set of N with NP equals plus 1, the residues, and T equals the set of N with NP equals minus the residues and the non-residues. So that's good. That gives you this very strong uniqueness result. That this way of thinking about the elements of ZP, partitioning it into two halves in such a way that it's going to act like the positives and act like the negatives in terms of their multiplicative structure, there is only one way of doing that. For the residues is this set which mimics the positives, and all the non-residues is this set which mimics the negatives. There isn't like a whole host of different ways of doing it. Is that okay? Questions? So is this a cryptography tutorial week or number? No, it's a number theory tutorial week. So in the tutorials this week, I'd like to look at some of the questions that we haven't done. So we did all of question 3. So it's question 2. Question 3 I've done all the parts of in the lectures. So question 2 on summations of various summations involving the Legendre symbol. And then in these exercises here, in the previous set of exercises, well, we'll just revisit anything that still needs attention there. In particular, practicing that evaluation procedure for evaluating the Legendre symbol. But once we've dealt with those, that'll be more or less all the material dealt with. And then for the final 2 weeks, then we can look at some past paper problems and revisit any particular areas or topics that you'd like.